Okay. So well, that's a problem because I need to manually launch my animations. So this tool doesn't work really often. So thank you again, the organizers, for inviting me. And today I'll speak about something different, mostly from the general topic of the conference. I'll speak about this huge brightening events that are often seen in young low mass stars. They are known as Eduard eruptions. First, that often happens to my family name. I have seen at least 3 different spellings of my name. So this is the correct one. So if you go back and try to look like this in the ADS, you'll probably see 0, or who the heck this guy is. So please, this is my correct name. And let's first review the main stages of star and planet formation. The story starts from a giant molecular cloud, and to whatever reason, turbulence or other reasons, some dense cores can appear within this giant cloud. These cores can become gravitationally unstable. They collapse under their own gravity to form the central star and a circumstellar disk. And then this stage is often called the protostellar stage or embedded stage, because there is an envelope, a remnant of the core, which accretes mainly onto the disk, and the matter is transported through the outer edges of the disk towards the star through the disk. And this is also called the main accretion phase, because here the most mass of the star is accumulated, about 95%. And then once the envelope disappears, disperses basically, and then the system enters the Titori stage, where we have a star and a disk, and somewhere here planet formation starts, and we don't really know whether it's here or here. And then once the disk again disappears, disperses, then the system enters the pre-main sequence stage. And these 2 panels are highlighted, and this is where we have accretion on the protostar. And this accretion phase lasts for a few million years, whereas the entire process of star and planet formation lasts for tens of million years. So it's a small fraction of the entire pre-main sequence stage. However, it has a definitive effect on the subsequent evolution. So what is the character of mass accretion on protostars? And historically, people believed it's sort of a steady or steadily declining with time accretion. And when I speak about steady accretion, I speak about like variations on time scales of years, tens of years, hundreds of years. I don't speak about small scale variations, about days or months. However, an alternative is a variable accretion with episodic burst, which was motivated by the discovery of a few Orionis object. We have heard already several times about this Orionis type eruptions. So Hartmann, Kenyon and Hartmann suggested that this is a schematic view of our embedded object. Have a star in the center, disk, and then unfolding envelope. The envelope mainly falls on the outer edges of the disk and then transported somehow through the disk due to viscous or gravitational torques towards the star, but it's not transported in a steady fashion. Instead, there is some dead zone here where the rate of transport is lower than in the rest of the disk, and the matter accumulates here. So it accumulates here until something happens, and this matter is dumped onto the star, causing a huge outburst. So this is illustrated here. Again, the mass accretion rate as a function of time. We see there's a burst. So this is a sketch, which is a purely empirical sketch at that time. And the dashed line shows the envelope inflow rate. So it was already at that time envisioned that at least some of the bursts should happen in the embedded phase when there is still envelope, and some smaller fraction of a few hours should occur in the titory stage of the evolution. And then this is all gone, and we see only a small flickering, and the accretion rate decreases. There are at least several mechanisms that can explain this phenomenon. One we have heard just in the morning. This is a fairly new mechanism, convection, convective instability in the inner disk. There are other mechanisms, thermal instability, tidal effects during close encounters, the magnetic rotation instability, accretion of dense clumps in a gravitationally stable disk. And I'll briefly review some of these mechanisms for your convenience. So this is something, I'm a proponent of this mechanism. We first discovered that with Shantanu Basu in 2005. And this mechanism involves formation of gaseous clubs due to gravitational fragmentation in the outer parts of the disk. And these clumps then migrate onto the star, produce the bursts. So how does it happen? First, what is gravitational instability? So we have a gaseous disk orbiting the central star. Then if the so-called Tomura Q parameter is less than about 1.52, then the disk becomes unstable in the sense that it starts developing spiral arms. It means if you give it any small perturbation, any noise, it's unstable. The perturbation grows and forms in otherwise axisymmetric disk. It forms a spiral structure. However, this is not the end of the story. That might have been the end of the story in the galactic stellar disks. And we see this phenomenon there as well. However, for the gaseous disk and circumstellar disks, the process can go further if the product of the cooling time times the local Keplerian velocity is smaller than a certain number. So what does it mean? If the cooling rate is faster the disk, and then these clumps can migrate onto the star and produce outbursts. I'll show it here in this animation. So this is a disk, some of our simulations. You see the central star, it's schematically shown by this circle. We have a sink cell here. So it's already in the midst of simulation when several fragments have formed in the disk, and the bottom panel is the mass accretion rate. Mass accretion rate through the central sink cell. And let's try to play this.
Sorry, in units, in which units?
Units of astronomical units. These are scales. These are 10 to the minus 5 solar masses per year.
This is mega year.
This is mega year. Continuous orbiting. So some of the clump can survive, not for long in this simulation. And after that, the other clumps continue flying around as nothing have happened. Another simulation also shows now there is a protoplanet, really formed protoplanet here, and it has opened already a gap. You see this a gap in the disk, and again, this protoplanet can periodically, it's on an eccentric orbit, and as it approaches closer to the star, it can lose part of its atmosphere and also produce a burst. So let's see it again. So it's you see that as it comes closer, it becomes compact. As it goes further from the star, it blows, basically expands. But one of these approaches closer to the star, it can lose part of the atmosphere and produce a burst. And this actually happens, repeats through the evolution several times. I think it's going to be one of these. Yeah, hop, you see. and then some afterwards another one, and this goes on and goes on. So because the protoplanet accretes gas from the outer disk as it goes through this gap, but then it periodically loses it during this close encounter. So that produces these periodic bursts. Let's go further. So yet another model is magnetorotation and stability. So this model exploits a sharp dependence of ionization rate on the gas temperature. And MRI is supposed to be ignited if the ionization rate rises above certain value. And that means it's ignited if temperature rises above a certain value. This critical temperature is usually invoked like 1500, 1400 Kelvin. And this is a schematic view of the disk. Again, the central star. The most inner parts temperatures are higher than the critical one. So it's MRI active. But then as we go further out of the disk, further out from the star, then we meet this region which is called the dead zone, when the temperature is lower than the critical temperature. And then the midplane is MRI dead. So basically only the outer regions can be. But and this also a very dense region because of that the non-thermal ionization due to cosmic rays, for instance, cannot do the job. So the ionization rate is very low here. But as we still go further out, we enter a region where the cosmic rays can ionize again the bulk of the disk, and then MRI can be active here. Or alternatively, if we don't believe in the MRI, that it can operate on secular scales or time scales of million years, we can invoke the gravitational stability here. So what is happening, whatever is active there, MRI or GI, is pushing matter due to the torques, or either viscous torques or gravitational torques towards the star. But as it comes closer, it hits this dead region, dead zone, and the matter starts accumulating there. As it accumulates there, even a small residual viscosity there, which is always present, would mean that this region will heat up, because it's a very thick, optically thick region. The heat that is released in the midplane stays there. So the midplane is gradually heating up and boiling until the temperature exceeds the critical temperature, and the MRI is ignited, and the entire region, this several AU, is damped onto the star. And that produces a burst. And we heard yesterday that this mechanism can explain this metal-rich winds. I agree, because here this is dead zone where dust particles also accumulate. So once this region is dumped on the star, we can really see this metal-rich winds, but at the same time it must be accompanied by a burst, as I will show later. So again, the MRI dead region is usually characterized by Shakura-Suyana viscous parameter about 10 to the minus 4, 10 to the minus 5, whereas the MRI active is about 10 to the minus 2. So let's see how this works on the animation. Again, this is the surface density. This is a very inner region. Scale is 2 AU, so it's about like 5 AU here. We are again looking, now we are looking at the very inner regions. In the opposite case, we are looking like large scale clouds flying from outside, from out to inside. Now we are focused on the very inner disk region, several AU. So this is a dead zone. This very dense ring is a dead zone. You can immediately see it's cold here. This is temperature. It's cold. Only the very inner regions are relatively hot here. And this is alpha, the effective alpha, viscous alpha. And again, it's very low, 10 to the minus 4, even lower. So let's, and here we'll see the mass accretion rate. Okay, so now it goes. The mass accretion rate is 10 to the minus 6, relatively low for a young system. And, but with time, matter accumulates there, and the temperature will gradually increase until the MRI is ignited, and alpha will jump to 10 to the minus 2 here. So let's watch it. It's going to happen very soon. Now you see the temperature is rising here. Yes, poof, alpha is large. There is a burst. All matter is gone. The ring is gone. It's gone onto the star, producing an outburst. And then it's cleared, and the process repeats. Now, slowly, the dead zone will regenerate, will gain mass, and the burst will reignite it. Of course, that will not last forever. So the frequency of the burst decreases with time. Yet another mechanism is a collision or close encounter of an intruder star with a disk. So now we simulated what you see here again. This is the gas disk, this is the dust, and this is the temperature, gas temperature. We put an intruder at some 3,000 astronomical units from the disk. This is a very deep scale. I mean, let's say 8 orders of magnitude, so don't be confused. It looks like a huge disk. In fact, it's really like we made it a very deep image to see the trajectory of the intruder. And at the bottom, you'll see 2 curves. One on the accretion rate onto the intruder, which is here, and one on the accretion rate on the target. So let's see what's going to happen in this case. Nothing going to happen? Yes, I think it's... No? It's a headache. Aha, it's flying. So now the intruder is flying. It's coming, and you see this is the mass accretion rate on the intruder. As it comes close, it produces a burst. However, almost nothing happens to the target. So it's a very low perturbation, and then both accretion rates sort of converge. This is not the end of the story. Watch the blue line and watch here. Pach. There is another burst. So this is the MRI. Now was ignited in the disk of the target because the intruder perturbed the disk. The matter starts flying towards the central disk, and that produces an MRI burst. Okay, the second part of the talk now. What are the consequences for this burst for the star? So there are many consequences for the disk. It can heat up the disk. We have heard already about several consequences. Can move the snow lines, can affect the chemical composition of the disk, or many, many, many things. However, the burst can also affect the star. And it's usually ignored. The effect is also very interesting. So what we did, we took a number of models, derived the mass accretion histories for this model, starting from solar mass stars down to upper mass brown dwarfs. And these are mass accretion histories as a function of time. This is a log in million years. So the black lines, they show mass accretion rates. They're sort of steadily declining with time. There is some small variability, but not as huge as was shown in the indicated with the blue color. Here there are cases where the mass accretion rate is really crazy. It shows large amplitude variations. But again, look at the scales. These are million years, so these are variations about tens, hundreds, or even thousands of years. So let's, what we did with this, why I cannot push it further. Okay, so we took all these mass accretion rate histories derived from simulations and post-processed them with the 1D stellar code. This is a stellar evolution code by York and Bodenheimer. And we derived the stellar evolution tracks: photospheric luminosity, accretion luminosity, effective temperature. So the initial seed parameters that we took for the star is 5 masses, 5 Jupiter mass, radius is 3 Jupiter masses, and the final stellar masses range from brown dwarf to upper mass solar, like 1.3 solar mass stars. And we evolved all that, all our stars up to 25 million years. One important parameter when doing this sort of exercise is the accretion energy absorbed by the star. So it is given by this formula. This is the potential energy, the rate of potential energy which is transported with the matter as it is accreted on the star. And there is some uncertain factor here, which is called the thermal efficiency of accretion, this epsilon. This tells us how much of this accretion energy is actually absorbed by the star and how much is radiated away. There are several cases that can be considered. One is so-called cold accretion. In this case, virtually nothing is absorbed by the star, and everything is radiated away. Only matter is absorbed. Energy is not absorbed. The opposite case, hot accretion, when some fraction, some non-zero fraction is absorbed by the star. We choose 0.2 in this case, and it can be interpreted, these two limiting cases can be interpreted like if there is a low mass accretion rate, then the matter will be accreted through magnetospheric tubes. And that means that the area covered by these magnetospheric tubes, the area of the star, is much, much smaller than the total area of the star. And that means that this energy can be easily radiated away. However, if the accretion rate is large, like during a Furore eruption, 10 to the minus 5, 10 to the minus 4 solar masses per year, then these magnetospheric tubes can be crushed. The magnetic field can be, magnetic field lines can be very complex, and the matter can fly all the way towards the star and actually envelope the star. There were some simulations of this, hydrodynamic simulations, and that means that there will be difficulty now for the matter to be radiated away. So some of the for the energy to be radiated away. So some of the energy will be absorbed by the star. We actually proposed a combination of these two, a hybrid accretion, which means that accretion is cold if the mass accretion rate is smaller than 10 to the minus 5, and it is hot when the mass accretion rate is larger than 10 to the minus 5. So what is happening now? What you see here is this the HR diagram, the total luminosity, effective temperature, and you can easily distinguish these tracks, stellar tracks here. The first messy, the blue color is the color is the age again in log of million years. So this is messy, but then you can see these tracks clearly, and they cover our simulations. Again, cover this range. You can retrieve these tracks. This is the 0 age. That's 1 million year old, 10, 25 million old. But then look, something is happening here. So what is this? What is this? And these are actually excursions that are experienced by our stars during the outbursts and after their burst. And I plotted here. So this is like an example of one of those. So the star starts here, goes here, and then there is one outburst and it goes all the way. So there is this loop. And then it returns back and it goes like this. So this is, and we plotted here the lines here, the dashed lines that you can see this, red lines, are isomasses for intermediate mass stars, for young intermediate mass stars. And they start here and evolve. So what it means that during the outburst, the low mass stars go to the portion of the HR diagram where young intermediate mass stars sit. And you can principle, you can confuse them if you don't pay real close attention to whether this is an Ephorian outburst or it's just a young star, intermediate mass star. So again, these are isomasses of 7 to 2.5 solar masses, and these black squares show the time. So this is 80 years, 80 kiloyears, 160 kiloyears, so the interval of 80 kiloyears. So these are really young stars, so these are more older. And the shades of blue is where intermediate mass stars dominates, and the shades of gray is where the Ephori stars dominate. So really is part of this diagram, in part of the diagram, you may find an Ephori star rather than an intermediate mass star, young intermediate mass star. So what's the reason of this excursion? This shows the mass accretion rate during the outburst, and the top panel, the red line, is the total luminosity, photospheric plus accretion. But you can we also show separately this is the accretion luminosity and this is the photospheric luminosity. And one thing you can notice that accretion luminosity dominates in the early stages of the burst, but photospheric luminosity dominates in the later stages of the burst. This is because the star really bloats. The star really bloats. It heats up first, but then cools, but it bloats, and the photospheric luminosity becomes quite substantial. Again, a comparison now with the known force. Now we put here different force that we know from the work of this work. And here is the hybrid accretion. Again, we can see that we can reproduce at least part of this force. This is the case of cold accretion, by the way. So this is when no accretion energy is absorbed by the star. So now the excursions are vertical. They not go to the upper and left part, but just go up. We can still explain some of the burst in the framework of the cold accretion, but the hybrid accretion does a better job. So you can really explain. This is, by the way, Fiorionis here sitting. So we can reproduce this Fiorionis cell. So if you give me a few more minutes, I can cover this.
Formally, you have 2 minutes.
2 minutes.
And no questions.
That's too bad. But problem with determination of primary sequence ages. When we study the primary sequence stars, 2 approaches are usually invoked. First is what is done. People use the non-accretion models, so-called non-accretion models. What does it mean? You just make a star of a fixed mass, and it evolves. And if you go to the databases of, for instance, Isabel Baraf, that's what you will see there. They just make a star, one solar mass star, and they see how it evolves, and then derive isomasses and isochrons. However, this is not how stars are born. The stars are born from a seed, which is about 5 Jupiter mass. Nobody knows how big it is. But the star is born very small, and then it accretes mass. And then it accretes mass, and if you try to calculate this accreting models, then you'll see that your results may differ from the non-accreting models of stellar evolution. And this is what I illustrate in the last slide here for the case of the hybrid accretion and cold accretion. The blue stars are our models at 1 million year old. So they are all 1 million year old. We put it again on the HR diagram. And then we try to approximate the fit this data with non-accreting isochrons. Non-accreting isochrons. So This is 1 million year old, and this is 1.5 million year old. So it means that the best fit now is for although the objects are 1 million year old, you make a conclusion that they are 1.5 million year old. So 50% wrong. Not so bad, but this is hybrid accretion. What if accretion is cold? Then these are again 1 million year old objects. You use again fitting using the non-accreting isochrones, and you come to a conclusion that they are 4.5 million year old. You are wrong by a factor of 1.5. This is a huge problem. I mean, this is preposterous. We just change one parameter, epsilon, and we can get such a different outcome. I mean, there is no solution to that. That's why people just all use this non-accreting isochrones because otherwise you have to admit that all ages that you derive, if accretion is cold, are wrong, at least for young objects. If you go to 10 million year old, 25 million year old, then it's better, much better. But 1 million year old objects, if you just, when I see someone is saying, oh, this star is 1 million year old, how did you know that? I use this Vorobyev, it's isochrones or whatever else isochrones, non-accreting isochrones. I say, wait a minute. I can trust like 10 million year old, but not 1 million year old. No. That's. And by the way, the same result, this we use the Stella code, and same was derived with Isabel Vorobyev code. So this is confirmed with different codes, Stella evolution codes. There is no solution to this, easy solution. All right, again, summary of the talk. There are many mechanisms and that can produce this a priori type eruptions. We are working now on distinguishing between them based on the kinematical signatures, based on the structural signatures, trying to figure out if this can be these outbursts can be distinguished from the observation point of view in the sense of the disk dynamics. And the low mass stars in the outburst then experience this, these excursions, and then potentially can present a problem for the calculation of the IMF. Just go to a young stellar cluster, 1 million old or even younger. You just count the number of stars, put it on the HR diagram, and don't really pay much attention whether this is a priori or not. And then you may have excess of intermediate mass stars there because you falsely counted a few oris in eruption there. And again, this epsilon parameter, the thermal efficiency of accretion, it's a poorly estimated. I don't know anybody who really did that calculation, and this has to be done somehow and to improve the age estimates of the stars. Okay, thank you.
So let's give time to questions, yeah? Okay, questions.
Thank you. I try to imagine what is a pre-Fior object. Is it a T-Tauri star with a clump of matter orbiting around? And could we observe this?
Which object? A Fior?
A pre-Fior. What is a pre-Fior object? Can we find this on the sky?
I think if we speak about the Fiori itself, its mass might be, the estimates of the disk mass. So when we for the clump mechanism to work, we have to have fairly massive disks. Actually, we do have most of the Fioris have fairly massive disks. Unfortunately, the case of FUORI itself is very peculiar. So the mass is not really high there. So I don't think that a fiori itself can be triggered by the clump in fall. However, other systems may be. I think that there are now observational campaigns to look into the structure of this. But I doubt. I think it might be a MRI, more likely, in that case.
Question or you ask? Okay. So,
So for a priori, there's claims that the inner subAU is optically thick, so the measured mass is only a lower limit. So it can be heavier.
yeah.
This is true that the mass estimates are very uncertain. And with the clumps, with the disk fragmentation continuing this point, many numerical simulations readily reproduce fragmentation. However, finding fragments is a huge headache. There is only one confirmed, to my knowledge, detection of a clump of disk fragmentation so far. But you have to keep in mind that it might be a selection effect, because this fragmentation occurs in the embedded phase. And then this disk is shrouded, and it's very difficult to observationally pinpoint this fragment, which is just several AU in size, maybe 5 AU in size.
More questions? Yeah. Okay, let it be the last one. Okay.
Eduard, the hybrid scenario, is it applicable only to the star with magnetosphere?
Without magnetosphere, perhaps the matter will be accreted through a thin layer, right? The boundary layer. And that would still be the area covered by the star. By this layer would be much smaller than the total surface area of the star. So it will be also applicable, I think, right, to the case of stars with low magnetic field.
It was the last question. Thank you very much. So the lunch time, and then 14:20, people who will visit Pulko Observatory collect some downstairs, yeah? Or here?
No, in the lobby. We were told in the lobby.
Okay.